Okay, thanks very much for the introduction. So I'm Wouter Zwierstra. I'm an assistant professor at the Utrecht University in the Netherlands, and thanks very much for the invitation. So I guess any talk on formal methods and the importance of program verification should start with the kind of obligatory Dijkstra quote, which says that programming testing can only be used to show the presence of bugs, but never to show their absence, right? So this is why we do formal verification. We can run our software, we can poke around and pass some inputs to our functions and click on some buttons and observe that something good is happening, but we can never rule out that something good is always going to happen or that something bad will never happen. Um, but curiously, there's actually another Turing Award winner who has other advice. So if you ask Donald Knuth, he has a famous quote where he writes that beware of bugs in the above code. I've only proved it correct. I haven't really tried it. So who should we believe here, right? Is it the Dijkstra or Knuth? And throughout this talk, I'll kind of bounce back and forth a little bit between unsoundness in theory and is it a problem in practice, or fixing a bug in theory and finding the same bug in practice. And the title of this talk is very much inspired by a very nice paper by Randy Pollock called How to Believe a Machine-Checked Proof. And in this paper, he has executes a thought experiment where someone shows up on his doorstep and hands him a USB stick or a floppy disk and says, here's a machine-checked proof of Fermat's last theorem. And then how can you convince yourself that this proof is actually right? And he goes through the various steps of what he believes is necessary in order to kind of trust that someone shows up out of the blue with this proof, what you need to do in order to believe this proof is actually true. And it covers a lot of the aspects that I want to kind of touch on today and that Jan and Marco touched on this morning. And I'll try to kind of talk about these three questions here. So the first is, when is a program correct and what does this even mean, right? And the second is, when it comes to formal verification, it's quite surprising in a way that we still find bugs in verified code. So if you think about it, it's a little bit awkward. What does that even mean? And then kind of speculating a little bit, or kind of saying something more about the more recent work and projects I've been involved in, is what can we do to ensure that a verified program really does work as the way we expect? And then some kind of more future perspectives. What can we do better? So first of all, when is a program correct? And typically, so this is also a picture of program verification in a nutshell, according to Dolly. And typically, when we talk about program verification, there's kind of three ingredients, right? We have a computer program of some sorts, and then we have a specification of this program in some formal logic, right? It's not enough to just have natural language to say sorts numbers or something. We really want something that we can reason about formally. And then finally, we have a formal proof in some logical system establishing that this program somehow satisfies its specification. So I want to go through all three of these points and ask some questions, right? So we start by saying the first ingredient was a computer program, but how do we even know what this program means and what is its semantics? And this seems like a pedantic question, or like it's obvious what the program means, right? I can run it and I can see what happens when I execute the code that gets generated. But really, if you think about it, we spend so much time talking about programming language semantics, but there's very few realistic programming languages that have a very, very precise semantics that we can actually do mathematical reasoning about these things. And then on top of that, there's even fewer languages that have an implementation or a compiler, which is shown to be correct, right? Where it will take high-level code and then produce machine code somehow, which will behave the same as the source code that we provide to the compiler. And if you think about it a lot more, there's actually a lot of different things that can go wrong. And I'll touch on some of these, and Jan mentioned them already. If you think about, a cosmic ray shooting down from space and then flipping the one crucial bit, which causes my program to go wrong all of a sudden. I'll try not to worry about these things too much, though. So what's a specification? Typically, a specification is a description of what a program should do. And this is given in a formal logic, right? Um, and then we certainly have to worry that, okay, if we need to formalize this somehow, we have to write this in a way that the computer can understand the logical formula that we're presenting to it. And then we do have to worry about, is the logical formula or the logic that we're writing or the implementation of our logic that's running on our computer, is that correct? And a much harder question is, somehow we take these specifications for granted, right? You can think of a lot of classical Dijkstra style program derivations. You start with the specification and then you derive a program that satisfies that specification. But how do we know that the specification is right to begin with? How do we know there's not a bug in the specification? Actually, writing these specifications can be very, very hard. So uh, it's another kind of thing to be concerned about if you're worried about believing a formally verified program. And then the final ingredient is some kind of formal proof establishing that the program satisfies its specification. And you can immediately ask the question, well, what is such a proof? In what logical system is it written? If it's formally verified and machine checked, maybe parts of the proof are filled in automatically or semi-automatically. So how do we believe that the computer didn't make a mistake? Or how do we believe that the computer is doing the right thing? And to make matters really kind of bad in a way, if you worry about these things, formal proofs are not written in a way that they're kind of amenable for human consumption. It's kind of like trying to read machine code or something like that, right? You're trying to understand the kind of nitty-gritty details rather than understand, like, what are the main ideas and how does this proof tick? So this kind of, and then leads to the next point, of course. If we have somehow checked this proof, how do we believe that this machine check proof is actually correct? And that's something which Randy talks a lot about in his paper. I'll touch upon this briefly. So a little bit about my own work. So I've done a lot of work on programming languages based on type theory, right? So think of systems like Agda and Conc and Idris, Lean. So Jan mentioned some of these already in his talk. And what I like about these systems is where many verification approaches, they say, oh, you have your programming language, and then you look at a logic and which models parts of that programming language. And here, if you look at this whole list of questions that I had to worry about, like what about the programming language semantics? What is the logic? Things like this. Well, the programming language and the formal logic are exactly the same thing, right? It's one system in which we write our programs and we do our proofs. So conceptually, at least, this already reduces the room for error in a way, right? You don't have to answer questions about the semantics of the logic and semantics of the language separately. Unfortunately, there's still kind of a whole bunch of issues that remain and sources of unsoundness, and kind of both unsoundness in theory and unsoundness in practice. So I'll kind of say a little bit about why are there bugs in verified programs, and this is something which Jan already mentioned, right? Sometimes the language that you're working in is unsound. So the kind of granddaddy of all unsoundness issues is the very first kind of unpublished version of Per Martin Löf's A Theory of Types, kind of from 1971. Um, it said that the set of all sets is indeed a set. So this is kind of, if you know any formal logic, or if you've kind of heard of Russell's paradox, this is probably going to cause problems. And indeed, or pronounced differently, you might read this as the type of all types is a type. And this was kind of shown to be inconsistent the next year, right? And later, or much later, this was simplified even further by Tony Herkens. And all of these proofs they use have a certain flavor of Russell's paradox. It's not exactly Russell's paradox. Thierry Cocon gives a very nice, in the citation that Jan mentioned, gives a very nice kind of deconstruction which teases apart exactly why this breaks. So that's the bad news, right? It seems like if you're not careful, you've built an entire formal verification in an unsound system. But there's kind of two bits of good news here, actually. The one is that it's kind of relatively easy to fix. So one way to fix this is you build up what's called a universe hierarchy. Instead of saying, the type of all types is a type, you say the type of all types is something bigger. Lives in set one, type one, something bigger than just the set of all sets or the type of all types. And then we can iterate this. So because the next obvious question is, okay, so what's the type of set one? And then it's this new thing called set two. And this is kind of stratifies or kind of layers all these increasingly big types. And then usually as a programmer, you just stick to set, or sometimes kind of venture into set one, but you never really need these huge constructions typically. And the kind of even better news is that it's really unlikely that you'll run into this problem accidentally. So this is the kind of approach that Idris takes, where they say, we know it's unsound, but unless you're looking for trouble, you're not going to find it. So this is a completely satisfactory and very pragmatic approach, and saying, well, we can work in an unsound theory, but it's only unsound in this kind of gnarly corner. And unless you're a logician, you're probably not going to run into that problem. So interestingly, right, it seems like we've looked at this problem, we have this problem, the kind of Russell's paradox kind of issues. And then you'd think that this, if you've solved this problem in theory, it kind of never shows up in practice. Well, here's an interesting story. In Agda, you can actually observe this, right? So Agda is one of these proof assistant / programming languages with dependent types built on type theory. And you might write a definition which says some variable x is equal to set. And then Agda would check for you that x is indeed lives in set one. So it seems this is kind of, and we can play this game with a new variable y and define that to be equal to set one, and then observe that y has type set two. So it seems like we're winning here, right? It seems like we solved the problem that we had initially. But there's an interesting issue on the Agda bug tracker recently, which said that here's another something I've defined called WTF, and it has set in this humongous number down there. And then Agda thought it had type set 0. So this is strange. And this is kind of an opportunity actually to prove falsity in your proof assistant. So this is really bad if this happens. In case you can't see why this would be the case, here's a little hint. This huge number happens to be 2 to the power 63 minus 1. And then incrementing that, and if you use a 63-bit wide positive number, you can see it wraps around and it goes back to 0. So it's kind of interesting to observe this, right? Where you start with an unsound theory, you come up with a fix, right? And you stratify your universes, you do this kind of very cleanly, and then you can still prove false because your implementation is using bounded width integers. So I'll go through a few of these examples of how you can actually prove falsity and where problems can show up. And here's an interesting kind of divergence slightly. So to make sure that Agda's logic is sound, all the programs that you write in Agda must be total functions. So that means you can't have missing cases. You can only write structurally recursive definitions. It's very precise about these things. And of course, it doesn't mean that you cannot talk about generally recursive programs. It just means that you can only run things for a finite number of steps. We have to be a little bit more careful about things. And consequence of that is that a program is guaranteed to terminate in finite time. And you'd think that these two properties would suffice, but that's not quite the case. So here's another kind of problem inspired by a little bit of theory, which has interesting practical consequences. So here's a data type I could define. It's called D, and it has one constructor. I'll call it the constructor lam, and it takes a function from D to D to produce a new D. So if you know anything about untyped models of lambda calculus, D's kind of a domain, right? If you know anything about Dana Scott's work on models of untyped lambda calculus, what I'm doing here is taking the fixed point of the functor D to D, which is known to cause problems, to put things mildly. Um, but what I can do here is I can write a little function app which takes one of these d's and another one of these d's and applies. Sorry, this should read f applied to x rather than x. Sorry, that's a typo on the slide. X would type check, but it wouldn't be very interesting. It'd be a constant function in its second argument. I want to apply f to x to produce a new d. Because if I do this, I can start writing kind of well-known kind of non-terminating untyped lambda calculus expressions, right? If you've ever studied an untyped lambda calculus, you know you can do this little self-application trick and write, lambda x arrow x applied to x, and then if you take that thing and apply it to itself, you can reduce this forever and it never terminates. So to fix this, what Agda does is it has this extra check. It makes sure that whenever you write recursive data types, it checks that what's called the positivity checker, that the recursion only occurs to the right of arrows, not to the left of arrows. So this seems like, okay, done and dusted. This is another problem which is only of theoretical interest. Actually, if you write exactly the same code to Haskell, you have a problem when you even try to compile the code. So previous versions of Haskell actually diverged when you fed it this big omega program, basically. Nowadays, the compiler crashes. It's not that running the generated code crashes. It's actually trying to compile the code. It used to diverge or crash. Nowadays, it crashes. And you get this funny error message about, GHC panic, the impossible happened, something horribly wrong went wrong. And what happened here is kind of interesting. So the GHC, the Haskell compiler, is very good at inlining code and aggressively optimizing code, which is a good thing, right? You want to get efficient code when you feed it some high-level program. The thing is, though, that the GHC inliner and the simplifier and all the kind of optimization passes that GHC will try to do, they really look for non-recursive code. Because if your code isn't recursive, GHC thinks, well, then I can always make progress by kind of unfolding definitions and doing all the evaluations that I can, all the partial kind of simplifications that I can come up with, and then that's always going to be a win. But what I've done here is kind of trick GHC into taking a definition that didn't look recursive, but actually was. So in that way, GHC is horribly confused, and then the compiler either diverges or crashes. So these are kind of two examples of where theoretical problems actually have practical consequences. So in an ideal world, and when people try to sell programming languages based on type theory, they say, oh, this is such a great idea because you have a single language for your programs and proofs. And this is something I still firmly believe in, right? There's one thing they don't really say, that most people who work on these languages are very much interested in the theory behind them, right? When you look at things like homotopy type theory and all this kind of univalent foundations, there's all kinds of interesting work going on. There's very few people who are also interested in writing compilers for these languages. So I would argue that most systems do not have a very mature or fully fledged backend. Idris is one of the exceptions here, right? Which Jan also mentioned, where they actually want to pay a lot of attention to being able to run your code efficiently. Instead, most of these proof assistants, they have a kind of a bit of a trick where they say, well, we'll take the programs that you wrote in our proof assistant or programming language, and we'll just transpile them to other high-level languages, which are kind of similar. So these are languages like OCaml, Haskell, Scheme, or JavaScript. And then we'll kind of piggyback on all the hard compiler work that other people did for us. And this is a good idea. It works very well. But this process of transpilation or extraction, which I think is the COC terminology, is that you can tweak this and you can customize it. And this is an excellent source of introducing bugs into otherwise verified code. And this is a shame, right? Because what you're doing is all of this kind of transpiled code or generated code, it usually doesn't fit very smoothly with the language that you're targeting. So you often need to kind of massage it a little bit. Maybe you need to have a little shell script which renames some things, or an extra layer of code around the code that got generated. And this is a great way to kind of trigger unsoundness, even though you've done all the hard work of verifying your code. So here's a few points that I'll mention, that where extraction in Cork actually deletes proofs, and that's a good thing, usually. If you customize this extraction in interesting ways, it might invalidate proofs that you've done previously. And actually, all of this compilation and transpilation can really change a program's meaning. So I'll give a few examples of these points. So Koch has this very nice theory where they make a careful distinction between things which are computationally not important. These are called propositions, then they live in a separate type called prop. And they have this property that any computation that you write will never depend on a proposition, or the value that you produce will never depend on the proposition. So this is a good thing, right? You could imagine coming up with a untyped semantics somehow, right? Where all the propositions are deleted, and then you could never observe the difference between running with prop or running without prop. And this is a good thing because we typically don't want to carry around these proofs at runtime. They're computationally irrelevant. So that means that they can get erased, that whenever we generate Haskell code or we generate OCaml code, we never want to inspect this stuff. We never want to compute with this stuff, and we get actually more efficient code out. It also gives for a kind of a fairly clean separation between it's very much in the spirit of Coq, where your programming language is more simply typed. It's a bit it's you think of the Coq's programming language being pragmatically kind of a subset of OCaml, a very safe subset of OCaml, and then there's all kinds of logic built on top of that. So what I might do is I might define a function which takes the first element of a list and define it like this, and take some polymorphic list XS, and then a proof which says that X is not the empty list, because I want to kind of rule that out. And then I can, this is the safe tail rather than the safe head. It'll take the remainder of the list. And then what I could do is generate Haskell code for this program. And then I can fire up my Haskell code, run it into GHCI, and then I can call this function. And where previously I've kind of done this work to pass in this extra type argument, which would guarantee that if you try to pass in the empty list to this function, you'll get a type error. If I do this now in Haskell, all of a sudden my safe head function, which I kind of guaranteed would always be well behaved, now produces a runtime error. I get a funny error message which saying exception absurd case. So deleting the proofs was a good idea because the proofs don't matter computationally. Any valid result that gets produced by safe head will still be valid. But the proofs were there for a reason. I was actually using them to rule out certain ill-formed inputs. And I've lost that information by throwing them all away. And that seems like a bit of a shame. So here's another kind of example of where I can verify a program and then still have it fail. So I try to come up with the simplest possible example that I could come up with. So I had to start by defining a little inductive type for bits, and these are either capital O or capital I, representing 0 or 1. And then I can define a function which maps Booleans to bits. I check whether the Boolean is true, and if it's true, I return capital I, and if it's false, I return capital O. I return 1 or 0, depending on what the value of the Boolean is. And maybe I'm writing a little Boolean encoder, and then I want to serialize a whole bunch of data types to these bits. And I can do this over and over again. I want to prove that my serialization is safe. So if I serialize stuff and then read it back, I get back the thing I started with. You could imagine doing a project like that in Coq very easily. And here I might prove a little lemma about what happens when I encode true. And here's a one-line Coq proof saying that, well, if you encode the Boolean true, you get out the bit 1. And I can prove that just by reflexivity, doing some evaluation. Now, I've done this is all the verification that I want to do. I'm now very happy with my implementation. So what I'll do is I set my extraction language to Haskell, and then because I want this my encoding to not just work with these funny Coq data types, I have to teach Haskell about what the booleans are and say, oh, if you take Coq's bool type, which is this kind of inductive little bool here, please map that to Haskell's bool type with kind of constructors capital false and capital true rather than the constructors which Coq was using, namely lowercase true and lowercase false. And then I kind of ask Coq to generate Haskell code for me, and I can fire up my Haskell read eval print loop, and then I can ask what happens when I encode the Boolean true, and this is now running in Haskell, and then what I get out is O rather than I. So that's strange, because I've actually done a proof in Coq which guaranteed me that whenever I encode the Boolean true, that I get out I rather than O. So what went wrong here? This is quite surprising. It suddenly seems that I've managed to change the behavior of verified code. And what went wrong here was the extraction part, right? When I was interfacing between Coq's Booleans and Haskell Booleans, I kind of got the order mixed up. And all of a sudden, I managed to map Coq's false value to Haskell's true value and the other way around, right? Coq's true value got mapped to Haskell's false value. And this is kind of has to do with the line that I have over here, where I kind of have to pass in a bunch of strings saying, oh, please generate this kind of code. So this is maybe not terribly, I have to be a little bit evil to get this wrong, and it's easy to figure out once you encounter the problem. But it's kind of disappointing in a way, right? Where we think about these proof assistants as being a very safe and super disciplined environment. And then all of a sudden, kind of, I actually want to run stuff, and things immediately break. And then the third point that I wanted to mention is that compilation really might change the semantics of things. So if you erase proofs, for example, you might change a function strictness behavior. I can think of all kinds of optimizations where I might map, Coq's idealized piano numbers into 32-bit integers, and that all of a sudden I can have different behavior there. They behave differently. There's all kinds of clever tricks which the extraction mechanism tries to do for me. It tries to inline definitions, delete arguments which only have one inhabitant because they're not important, and then other transformations that actually might affect a program's performance, for better or for worse, who knows. And compilation might even change the type of a function. It's when you do things like delete arguments, which can only possibly be one value. So a lot of these points aren't very specific to Coq, but they're kind of illustrative of the issue that you have when people write proof assistants. They usually don't think about actually running the code that you write in these proof assistants. And we really need to do a better job to kind of tighten the integration here or write better backends for our proof assistants. So coming up with a better link between like the world of proof assistants and the world of programming languages. Even if these two things are the same on paper, and when you talk about type theory, they're really not the same in practice. So there's a lot of people working in this direction. So I know for Agda, for example, the people there have been working on a tool called Agda to HS, which is generating readable Agda code, Haskell code from Agda developments, which you can actually integrate cleanly with the rest of your development. So they do take a lot of care to look at some of the Haskell specific features here, things like type classes and show instances, the kind of things which you take for granted when you program in Haskell all the time, and kind of figure out how to model these things in Agda so that when you actually generate Haskell code from your Agda, you don't have to worry so much about, you don't have to do these funny kind of replace these constructors with these constructor kind of tricks. So I want to say a few things about something more recent that I've been working on in the context of another research project, and which has to do with certifying compilation, and in particular in the kind of smart contract setting. So I have Manuel Chakravarti, who also lives in Utrecht, and he works for IOHK, which is one of these big blockchain companies that you have these days. And he's working on a compiler which takes a subset of Haskell called Plutus TX, and then compiles this to a very, very kind of simple lambda calculus. And the idea behind this Plutus TX language is that it takes this subset of Haskell, and then you can use this to write smart contracts on this Cardano blockchain. And each smart contract is usually a simple-ish Haskell program, but it has this property that you write this in Haskell, it gets compiled to this very low-level Plutus core language, which is a variant of System F, basically. It's a lambda calculus with a type lambda calculus. And then once you kind of compiled it, you deploy this on the blockchain. And then once you've committed it to the blockchain, you can't change. There's no bug fixes that you can easily do. So you have to be sure that these programs are extremely well behaved. And you really want to know that if I, write code to the blockchain, is the code that I'm committing really correct? And the code that you have to commit is actually the hash of this huge system F or this huge lambda calculus term. And how do we know that there's not a bug in the Plutus compiler, right? How do we know that we started with this very simple Haskell program, but then we ended up with this huge term that kind of the core that we want to commit? And how do we know that these two things are doing the same thing? So this seems like a hard problem because Plutus TX is taking a subset of Haskell as its input, and it's using some of GHC, but actually all of the hard work is done by a series of optimization passes. So, and all this happens on what's called the peer, or Plutus's intermediate representation. And what we've done is we've tried to come up with an approach which doesn't involve, trying to do the full-blown verification of a compiler like GHC or even the Plutus compiler. And these are because they do all kinds of transformations. They're still under active development. And the approach that other compiler verification projects like Concert have taken is that, they write their own compiler in a proof assistant and they do all their reasoning there. Here we're trying to get like some soundness, even if we can't prove that the compiler works for every possible run. What we can do is we can at least make its behavior more transparent. So what the compiler does is it'll kind of generate the AST that it does before and after every pass. And then what we've tried to do is come up with a specification, or what we call a translation relation, characterizing what that compiler pass is doing. It might eliminate dead code, it might inline let bindings, it might thunk lazy definitions, or it might do all kinds of stuff. And I'll use this notation where I use this little triangle to relate two terms, right? Saying that this is the pre-term and this is the post-term. When we have some AST T-pre, which is transformed into something better, hopefully, called T-post. So what we do is we try to define the possible kind of behaviors of the compiler independently of the exact compiler implementation. And if we have this relation, and we take this as our specification, we take a run of the compiler, then we get a whole series of these ASDs, and then we can check whether each of the kind of steps in the compilation process was well behaved. So here's a little example of such a relation, which I've simplified very much. So it's a kind of very small lambda calculus, but it kind of gives a flavor for what we're looking for. So you can read these rules starting from the bottom, and then the first, 1, 2, 3, 4 are basically rules are all congruence rules. So this says that if the bodies of the lambdas are related, the lambdas are related. If the T1 is related to T1 prime and T2 is related to T2 prime, then we just have the congruence of application. The let rule also kind of follows congruences. It does one thing which is slightly interesting, is it adds the kind of let bound variable x to some environment that we're constructing gamma up here when we go into the body T2. Variables are just always related to themselves, but this is the only really interesting rule. And this one says that if we encounter a variable x and we happen to know that x is bound to some expression t prime by some previous let binding, and if we then can continue inlining around t prime and we get some term t out, then X is related to T. So crucially, this is a kind of non-deterministic relation that you can see here. Every time we can encounter a variable, we can say, oh, we're not going to change this variable, X stays X. Or if we encounter a variable, we can say, oh, we know that X is bound to some other term T prime, and let's go inline stuff in T prime and see what happens there. But it's fairly easy to check if you have two kind of ASTs, whether they're related through this inlining relation or not. So the good news here is that once we've nailed down this specification, we can actually reason about what the compiler is doing, right? So I would argue that this is now easy, in quotes, because it's not really easy. It's still a lot of hard work. But at least we've reduced the problem of reasoning about the actual compiler implementation, which has all kinds of clever stuff in it. For example, when it comes to this inliner, deciding when to inline a given variable, there's all kinds of heuristics that compilers have. They have these magic numbers which say if the expression is that big, inline it, and if it isn't, then you should. Or there's all kinds of checks that it does to make sure that to check whether inlining is sensible or not. Now, we don't have to worry about any of that stuff, but we tried to come up with an abstract characterization, a specification of what the compiler should be doing. And what we can then do is reason about this specification rather than the implementation. So that we want to show that for any terms P and Q, if they're related by this inlining relation, then they should have the same behavior. They should be contextually equivalent. And if we can prove this in Calc, then we know that any run of the compiler that adheres to its spec is preserving the program semantics. So this opens the door to kind of a little bit of certification work. So we can now check whether a program was compiled correctly easily enough. We run the compiler, we collect the intermediate ASTs, we check that every compiler pass has behaved according to its spec, and we can prove that every compiler pass is kind of correct once and for all. And then we don't have to worry about if the compiler changes something in its magic number about what it decides to inline something. The proof kind of is robust against that kind of change. And we can do even better, right? So this contextual equivalence is a super powerful property, right? It's saying that for any context C, if we know that P and Q are contextually equivalent, we can plug these into some program context and they'll behave the same. So in particular, suppose that I
Can you still hear us? Oh, we can no longer see a screen.
Okay, it seems. Let me share screen. Thanks for letting me know.
Okay, it works now.
It works again? Great.
Yeah.
I'm not sure why the connection dropped. Okay, so here's a context which I would argue checks whether P holds. And because my programs little p and little q are contextually equivalent, this context won't distinguish them. So if I believe for whatever reason, and that my input program little p satisfies the property big P, then if I can trust the contextual equivalence result, then I know that Q will also satisfy big P. So this is interesting, right? Because this contextual equivalence gives us a way to transport proofs independently of the technology using to reason about the surface level stuff. Okay, so finally, can we do better? If you think about all the assumptions that we're making, it's easy to get very depressed. To believe a verified program works, we're kind of assuming the correctness of the hardware, the operating system, the software to render the program and the proof files, the correctness of the parser that reads in these files, the compiler that we're using to generate executable machine code, the correctness of the proof checker. Everything could be broken. So if you think about it, it's kind of a miracle that any of this works at all. So is there any hope? Well, it seems kind of infeasible to try and verify all the things, right? And Randy, in his paper, says the entire technology stack is kind of too complex to believe by direct understanding. There's no way you can kind of absorb uh, all of a modern computer architecture up into the compiler and everything in between. Um, the good news is the situation isn't quite so bad because we have a lot of empirical evidence that stuff is working, right? If we compile stuff using different compilers and we don't observe any difference, or we run on different operating systems or different architectures, different times of the day, it's highly unlikely that any bug that kind of is lurking there is exploiting any particular feature of the compiler that we're running. If we kind of, it'd be a very big coincidence if two compilers had exactly the same bug. So verified software can break. That's the bad news, right? Writing formal specifications is hard. There might be a mistake in the spec. Writing verified compilers is something that no one really does. There's programs don't exist in isolation. How can we be sure that our verified code is called the way that we expect? And programs aren't executed in isolation, right? The network might drop, my screen can stop sharing, the database can go down. And even if you're kind of running a verified program and someone just pulls the plug out of your computer, it still calls it to fail, no matter how much work you've done in the verification. So in the last 2 minutes, I want to kind of offer at least some perspectives, right? Type theory is a language for programs and proofs. And that's at least gives me hope, right? If we write these specifications in our language, and we write a specification for the function that we're interested in, we at least have a formal object that we can reason with. So why not turn this into a dynamic test as well? So you could imagine taking some specification S, which is a relation between functions inputs and outputs, and turning it into some check, which you feed an A and a B, and it checks whether this is true or not. And there's certain tools like quick check for Coq, which are really heading in this direction. So then you could imagine that we can actually enrich extracted code that we've reasoned about with contracts, that we actually kind of, that the program behaves the way we expect it when we actually execute the code. And if we erase proofs, like even the safehead example, we still get a dynamic failure, but it's clear whose mistake it was. It was the function that called safehead without checking the list was empty. So formal verification is really not enough, right? If we and formal verification is interesting if you think about it, right? We write unit tests all the time to check the functional correctness of one piece of code, but then formal verification kind of says, well, we can ensure that this code is always well behaved, so we no longer need to run our unit tests. But software testing doesn't just write unit tests. You typically want to do integration testing. Does the entire system behave in a sensible way? But where's the kind of corresponding thing that we can do when it comes to verification? When it comes to verification, we're still kind of stuck in the unit test level where we say, oh, this function is well behaved. But how do we prove that some composition of verified function, even from different systems or different proof of systems, are all kind of fit together nicely? So if there's one approach that can kind of tackle this challenge, it has to be type theory for me, right? We can program and prove whatever we like. So we could do things like model the types of another language, and we can write generic programs that kind of marshal data back and forth, and we can check data integrity dynamically and fail predictably whenever we encounter errors. And all of this is possible in theory. And this won't fix all the problems, right? We won't rule out all failures. But if we kind of figure out exactly where to put the inevitable dynamic checks and make sure that we do them, and then we learn that when they succeed, we have the information that kind of the rest of the program will execute safely. That's already valuable. So a few conclusions to wrap up. So verified programs can still go wrong, and not just for one reason, for countless reasons. And software today is so complex that we kind of have to give up on writing flawless code with an empty, trusted code base. That's always going to be a pipe dream. But if we kind of accept this imperfection, there's still a lot of fun to be had. And I kind of wanted to convey some of that to you today. So here's a few of the things that I mentioned, and I'm happy to take questions. I'll put the slides on my website as well, but thanks for listening.
We may have time for one fast question.
Okay. Let me stop sharing my screen so Yannick can get set up.
This one, right?
Yeah.
Okay, thank you for the very interesting talk. I
Thank you.
really enjoyed the Agda universe overflow example, and I wanted to ask you, so if we can do such a thing in Agda, then would you say that like the way it structures its universes is actually better than what Idris does? In the sense that if there is this overflow, then I mean we essentially have the very same thing that Idris has, right? We're just removing.
Yeah, so kind of they're logically equivalent, but maybe not pragmatically, right? I mean, in order to trigger the overflow, you really have to do quite some work. And then in order to, after you've triggered the overflow, still run into the kind of Russell's paradox, like or Girard's paradox situation, and prove falsity. You're never going to do that unless you're looking for trouble. So I just arguably maybe there's other easier unsoundness proofs involving set in set. Probably not, but who knows? So, but it's fine, right? Like I said, I guess my position really is that you won't accidentally write these kind of programs. You won't actually write unsoundness proofs accidentally by exploiting that particular feature of type theory.
Mm-hmm. Okay, I see. Thanks.
Yeah.